Hello, my name is Isabel Andrade, and this is my lab report on constant velocity. Throughout this report, I will go over an introduction to the lab, reviewing the purpose of the lab and some essential principles. Then I will analyze the motion of the object as seen through the video on the tracker, and then I will discuss some computational models created through GlowScript. Then I will analyze the difference between the observed and predicted graphs, and lastly, I will conclude this report by answering what-if questions regarding the lab. The purpose of this lab is to record the motion of an object moving horizontally without changing directions and with a constant velocity. Then, by analyzing this video, we're able to see the position of the object with its corresponding time. And this allows us to create an observed graph using that data, and then with a computational model using data calculated through GlowScript, we're able to use the fundamental principles of physics to observe the difference between a calculated model and an observed model. And from this results, an overview of the graphs include that the slope between both graphs were very similar during the first few seconds, but then as the time increased, the slope of the observed graph began to vary from that of the computational one. For this lab, we will be applying some fundamental principles such as Newton's first law, which states that an object in motion stays in motion unless acted upon by an external force, and likewise an object at rest remains at rest. This coincides with the idea of constant velocity, which is created by having a net force of 0. Therefore, if there are no external forces acting upon an object, creating a net force of 0, then the object will remain in its consistent motion. Then we are also applying Newton's second law, which states that an object is dependent on the net force acting on the object and the mass of the object. Through this law, we are able to derive the following formulas of acceleration and velocity update formula, which further elaborates on our understanding that if we have a net force of 0, creating a constant velocity, then we will not have an acceleration, nor will we have a change in velocity, creating our final velocity equal to our initial velocity. For this lab, I chose a tennis ball as my object. As you can see in the image, I placed the origin of the coordinate system to start at the center of my object, with the positive x direction going to the right and negative x direction going to the left. Additionally, I established the diameter of my ball to be 0.0658 meters, as shown by the blue line. In order to analyze the object, the video was trimmed to start once the object was already in motion, thus following Newton's first law, so that no initial acceleration or final deceleration was calculated for. As the ball is moving to the left, it creates a downward slope, as you can see in the graph on the top right corner, which is establishing the position versus time graph of the observed motion. GlowScript was used in order to create a computational model. To properly analyze the object, the initial position of the ball was recorded from the tracker video. Then the initial velocity was calculated by using the formula change in position over change in time, using the first 2 frames of the video to collect the position and timestamps. Although the mass of the object was inputted into the code, this would either way not affect the calculations because, since there is constant velocity, it would not be impacted by the mass of the object. Then, in order to establish a while loop that would go through the iterations of analyzing the position and velocity of the object in intervals of 0.01 seconds, the time could not be greater than 0.63 seconds, which was the final time of the tracker video. And lastly, I used the position and velocity formulas as you can see in the table above and converted them into the code form in order to properly use them within my while loop. As you can see, my code is here, but in the link below you can also see the full code. By running this code, we got the following simulation of an object moving horizontally at a constant velocity. As you can see, the position versus time graph has a downward consistent slope, which means there is no change in acceleration on the object, thus meaning that there is a net force of 0. In this graph, I have inputted the observed data from the tracker video and the computational data from the GlowScript. By looking at the graph, we can see that both lines have a very similar slope during the first few timestamps. The object is calculated to be traveling at similar velocities. However, after about 0.2 seconds, there begins to grow a discrepancy between the slopes of the lines. It can be seen that the slope of the observed position is decreasing in value, while the slope of the computational position is remaining consistent throughout. This error can be due to outside forces on the observed object that were not accounted for. For example, the frictional force that is acting upon the object as it is moving along the surface can cause the velocity of the object to decrease. Additionally, any other forces such as wind may also create a drag on the object, decreasing in acceleration. Because the computational model eliminates any of these unaccounted forces, it enables it to calculate a constant velocity. However, the observed graph has some discrepancies that prevent it from being perfectly constant. After completing this lab, there are some analytical questions that arise. For example, if I were to have changed the orientation of the axis, would this change the data? Well, the only thing that would be changed would be the direction of the slope of the position graph. Instead of the object moving negatively, it would be moving positively, thus having an upward slope and creating a positive velocity. However, this would not impact the actual data because the slopes of the graphs would be equal in absolute value. Another question that rises is the idea behind the net force. Because the object was in motion in the world, there are various forces that may not be able to account for. In the vertical direction, there is gravitational force that pulls the object down and normal force that pulls it up. However, there are many outside forces in the horizontal direction that could be implicated, such as frictional force and air resistance. In a future lab, this discrepancy could be improved by using an object that has a low coefficient of friction or by implementing a friction force into a computational model to better correlate to the observed graph. Thank you.